Welcome to Inside Personal Growth Podcast. Deep dive with us as we unlock the secrets to personal development, empowering you to thrive. Here, growth isn't just a goal, it's a journey. Tune in, transform, and take your life to the next level by listening to just one of our podcasts. Welcome back to Inside Personal Growth. This is Greg Voisen, the host of Inside Personal Growth. I'm joining you from Encinitas, California, and on the other side of the world is Frank Ladd, and Frank is joining us from Christchurch, New Zealand, and he's going to be speaking with us about his new book called Just Plain Wrong. Now, Frank, how are you doing this morning? It's morning there, it's afternoon here in Southern California.
That's all right. Hey, good. I'm rocking over here. Everything's good. A little bit of a drink, but we're fine, yeah.
I'm glad that you are. And I'm going to let the listeners know a little bit about you. He's an advocate of the constructive mathematical viewpoint of Bruno Di Finetti. Frank Ladd is a research associate at the Department of Mathematics and Statistics, the University of Canterbury. He's the author of Operational Subjective Statistical Methods, a mathematical, philosophical, and a historical introduction, which was a Wiley book in 1996. Many journal publications in mathematics statistics are available on this pages at the researchgate.net. That's researchgate.net. These include Extropy, Complementary Dual of Entropy, Statistical Science 2015. He's also the lecturer widely thought around the world, residing in Christchurch, as I said. And over there, he's got a very relaxed life. Well, Frank, thank you for taking this time today to be on Inside Personal Growth and talk about your new book. The total title of this book is Just Plain Wrong, the Dalliance of Quantum Theory, and the Defiance of Bell's Inequality. So for those of you who are going, wow, how is Voisen? Has he gone mad? And he's interviewing Frank. I am, because sometimes I'm switching things up, and I think there's a lot that people can learn about you, your book, and what's going on. So really, Frank, let's start off with that. What really inspired you to write this book? Was there a specific moment or discovery that really prompted the evolution of this book?
Sure, yes. There was very specific. It was professionally, I'm a mathematician, and I'm mainly interested in probability. That's my biggest fundamental interest. And one time I was at a party recently, not recently, it's 10 years ago now, where I met an old friend I hadn't seen him for 40 years, I think. But he, from graduate school days, he was a friend of my brother's, blah, blah, blah. And from graduate school days, he, he had similar background to myself. He was a quality control engineer for a major corporation. But he told me that, hey, Frank, I was at the gym one time talking with a bunch of people, and I mentioned that I didn't know anything about quantum physics. And they said, oh, we don't know anything about it either. Let's start a study group. He said, so we started up the study group, and someone sorted out what are the topics that everybody should prepare for. He said, I got the topic of Bell's inequality, and it's actually a very interesting problem, and I think you should look into it. So he said, I've got notes. I did all the background reading myself. I'll let you know what it's all about. And so I said, sure, I'll look into it. And so we started correspondence, and that's how I got interested in the problem. I had never been interested in physics since high school. But, and the more I heard what physicists said about probability, the less interested I was. But I became interested in this problem.
Well, with your background in, as you said, mathematics and statistics, it obviously interested you. And your book really challenges widely accepted interpretations of quantum mechanics. And again, particularly Bell's inequality. Can you explain what you found to be, as you state, the title of this book, Just Plain Wrong, kind of in simple terms for the listeners? Because you're actually rebutting what someone came up with as their theory, and you're saying, no, it's wrong. So what's wrong about it? And are you able to explain that to our listeners in kind of a simple sense?
Sure, I can. I can explain what it's about. We'll need to talk a little bit of background of what physics is about. Physics is a study of how things work. Well, what do you mean? How do things work? How do things work at the scale of our life, like rolling bowling balls and figuring out structures of buildings? How much load can a joint carry and that sort of stuff? And then those at this scale, we're talking about things like meters and kilometers and centimeters and hundreds of kilometers. Well, there's also a scale of the planets and the universe, and there we're not talking about thousands of kilometers. We're talking about light years, billions of light years. These are huge, huge scales of time. And there's the astronomical scale. There's what's called the classical scale is the scale of our life. And then there's the quantum scale is the scale of tiny, tiny, tiny stuff. Okay, for example, we're talking about things like photons and electrons. To get an idea of how tiny we're talking about, the mass of a photon, it's not grams or tenths of grams. It's 10 to the minus 48 power grams. That is 0.00000001 grams. We're talking about tiny, tiny, tiny stuff. How do things work down there? That's what quantum mechanics is about. Well, classical mechanics is the mechanics of bowling balls, and there are two features of it that are very important, that are different, apparently, from quantum mechanics. And the things that are different are the bowling balls. If we roll a bowling ball down an alley, going at the pins at this angle with this acceleration and spinning at this rate, the laws of physics will tell us what will happen. They'll say, well, if you do it like that, you're going to get a 6-10 split. If we get a 9-10 standing alone, or the laws of physics will tell you what happens. That's one feature. And the other feature is that if you're rolling your bowling ball and applying the laws of physics to your alley, you don't have to pay any attention to there's 50 alleys in this alley, and there's one immediately behind you where somebody's bowling balls in the opposite direction. You don't have to pay attention to that. That's a feature of what's going on in your alley. The mathematics of physics is local. It depends on what's going on here. Well, quantum physics, we're not rolling bowling balls down an alley. We're sending photons down long tunnels, 1 kilometer long tunnels. We send 2 photons in opposite directions to one observation station and to the other observation station. Not a million photons like you see coming out of your light bulb. Just a single photon. And when the photon gets to these 2 stations, it's going to meet a polarizing material, just like your sunglasses. Your sunglasses, some light comes through and some doesn't come through. What makes a photon go through and not go through? That's what quantum mechanics is about. And the features of the mathematics are different from classical mechanics in that the mathematics of quantum mechanics don't tell you whether the photon will go through the polarizer or not. They'll only tell you the probability that it will go through the polarizer. That's one feature of it. And the other feature is that it turns out if you're sending photons in opposite directions, well, as is currently understood, the activity of the photon at your polarizer depends on what's going on at the polarizer behind you. So they say that quantum mechanics are not local. This was a feature that Einstein had objected to in the 1930s, and that's how we get into Bell's inequality. But go ahead, yes.
Well, now my question is so if Bell's inequality, and I think you need to kind of explain that for the listeners because that's important. You're saying that his theory is faulty.
It's mistaken. Yeah.
It's mistaken, right? But it's going against, what's been around in the scientific community for a very, very long time. What is it why is correcting the misunderstanding so important for the scientific community and beyond? And what are the broader implications of his error?
Okay, so there's quite a number of questions there. So it goes like this. First, about Bell's inequality. If we do this experiment that we were just talking about, where he sent 2 photons in the opposite direction, what the experiment does, the experiment takes place very fast because these photons are traveling, of course, at the speed of light. Photons are light. Light is made up of pieces of stuff, little packets of energy, and they're going very fast. To do this experiment, setting them down 1 kilometer long tunnel, it takes 1 nanosecond. It's the whole time that this experiment takes place. And that's Bell's inequality was this. Einstein in the 1930s, he was concerned about these probabilities of quantum physics. He says, what are these probabilities? What are they? He said, the probabilities are correct. Yeah, he was involved in developing the mathematics, but he said, what are these probabilities? He says, I can't believe that the probabilities are in the photons. Probabilities are not part of nature. His famous saying was, I can't believe that God rolls dice. That is, that this nature is the result of a random experiment. He says that something's going on here. We don't know exactly what it is, and probabilities represent our uncertainty about what's going on. When we know some features of it, like we know the direction of the polarizers at the end of these two tunnels, we know that, but that's all that quantum physics is involved with. The probabilities don't represent the properties of the photons. They represent our uncertainties about things. Well, he got shouted down by Niels Bohr in what's called the Copenhagen view of quantum physics, and which became the standard view, and it's the general view, but many variations on these details. But that's the standard view. Well, in the 1960s, John Bell, he was a young Irish physicist, and he was a particle physicist. He worked at CERN, the Centre Européen de Recherche Nucléaire. See, that's where he worked, and he was interested in these things. He was interested in Einstein's views, and he's trying to reconstitute how it might be relevant. And he came upon this problem. There's an inequality of quantum physics of the quantum probabilities, that if Einstein was right about the locality of quantum behavior, which has been rejected, but if Einstein was right, then the probabilities of quantum physics, to which Einstein subscribed, seem to defy this inequality. And how the inequality works is, we have to think about an experiment it's actually an experiment that you cannot do. You can't do this experiment. These people were all Germans. It was called a Gedanken experiment, a thought experiment. Here's the experiment. You're sending the photon in opposite directions to station A and B, and polarizing material has a direction to it. Has a direction to it. You could set the direction of your polarizer up or down, or at any angle you want at A and any angle you want at B. Well, the polarizer, the experiment that you cannot do, you can send it to direction A and direction B. You can send it to direction A prime and direction B. You can send it to A prime and B prime. You can send it to A and B prime. You can send it to any one of these four directions, but you can't send them to all four at once. Well, suppose you could. That we're going to do a thought experiment. In that context, if you could do this polarizer, the result of the experiment, what are we going to see? The polarizers get set at one of these directional pairs, AB or AB prime or AB. It gets set at one of those, and once it's set, then we're going to observe. We have a photographic plates behind these polarizers, and we can tell, did the light go through or didn't it go through? A photon makes a little mark on the photographic plate. So what are we going to observe? Do the photons go through? Yes, 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 no, no, yes, no, no. Those are the four, and the quantum mechanics tells the probabilities of those four things. Well, yes, yes, and no, no are both represented by 1, and yes, no, and no, yes are represented by -1. So we do an experiment, and the result is going to be 1 or -1. Well, if you did all four experiments and you added those results together, you could get 4 plus 1s, 3 plus 1s, and 1 minus 1, 2 pluses and 2 minuses. If you did all four, well, if you set 4 different photons and did that experiment 4 times, the sum of those 4 things can be 4, 2, 0, -2, or -4. But if you did the experiment with the same pair of photons at all 4, this Gedanken experiment, they'll discover that the sum can only be 2 or -2. 2 or -2. Now, what's the result going to be? Well, it's random. The quantum mechanics tell the probability of 2 and the probability of -2, and they make an expectation of the sum. With the expectation of the sum better be between +2 and -2. It's some average of those two probabilities, and +2 and -2. The expectation better be between -2 and +2. Well, if quantum mechanics is not local, as Einstein claimed, then it appears that the expectation supplied by quantum mechanics is 2.8. It's not between -2 and +2. That is the defiance of Bell's inequality. And that is what that's what I'm claiming in this book is wrong. They made a mistake in coming up with 2.8.
So you're saying that's the mathematical error of neglect that you mention in the book.
They forgot to note. Well, the error of neglect is that if these four things can only add up, each of them is +1 or -1. If these four things can add up only to 2 or -2, that means that if you added 3 of them and you get it to sum to 3 because you got 1, 1, 1, well, then the fourth one's got to be -1 because it can only add up to 2 or -2. If you got a 1, 1, +1, +1, -1, and 3 sum up to only +1, then the fourth one's got to be +1 because it can only add up to 2 or -2, all four. That's the error of neglect. They forgot to notice that there are functional relations among the four components of the sum that is involved in
So in your community, the scientific community, why has this persisted in this discourse for so long? I mean, you were talking about, didn't you say the 1950s? I thought you said. Yeah. So we're now in 2025. Now you're saying that there's an error. Is anyone agreeing? Is anyone agreeing with you?
I'll answer that question because when the mistake was made, this mistake and neglect, the mistake was taken on as correct, and it came to be embedded deeper and deeper and deeper into the general understanding of quantum theory. In 1980, subsequent to John Bell, who published this paper in 1965, 1970 was John Clauser, who worked out the experiment just in the way we had mentioned. 1980, along comes Alain Aspect, and a French young guy also. He said, wait, this great result of quantum physics, it's based on a thought experiment. Can't we get any real experiments? Isn't this physics we're talking about? We're not talking about dreams. We're talking about physics. I'm going to make some experiments. So he did some experiments, and he did his experiments, and he concluded that, yes, he did his experiments, and he found out that the answer was 2.8. Just as Bell's inequality said. Well, that was taken as correct, and then it was even expanded more and more and more. And the things that I have noticed, the physicists have not studied them because they rely on, once things get published in a paper, then people all refer to this paper. There's this paper, and that comes to be common knowledge. So people know, everybody knows. If I send my papers to the journal, American Physical Society journals, the editor won't even send it out for review because they say, we already know about this. You got to be crazy. These three people have won the Nobel Prize for this. We know about this. I'm not going to send this out for review. I'm not going to bother my reviewers to read this stuff that I know is wrong. We all know it's wrong because they're interested by the magnificence.
It's entered the establishment, but it's true what you say, that it is wrong.
It is wrong.
You critique Nobel Prize winning research in the book. And so I applaud you for your willingness to take this challenge on, because it would seem like it's an uphill battle. But how does your approach challenge such, I hear what you're saying, highly regarded work that's been done, and as you said, it's been established, but people didn't oversaw what really was happening. In other words, it's almost like they didn't try the experiment themselves like this other scientist did and prove that they were wrong. So you do have some people in your camp, right?
That's not true. Many people have done this experiment. They've done it in different ways with embellishments on it and blah, blah, blah. And they've all made the same
conclusion. The same conclusion. And they're all saying that it is just plain wrong too.
Not just the same conclusion, the same mistake. The same mistake is that there's an error of neglect, that they neglected the functional relations. It's a mathematical mistake. And if you know basic mathematics at the college level, you will see the mistake very simply, very clearly. If you're not familiar with the mathematics, still people would be interested in and should be willing to know that even scientists can make mistakes. We can make mistakes. We make mistakes also. Everybody makes mistakes. Well, science, they've made a mistake and it's become embedded into physical theory because of the enamor of the great the glories of these great physicists.
Yeah, I can imagine that they've won prizes, Nobel Prize.
The great physicists never interested me. What interested me was the problem. I didn't know these physicists were great when I started studying the problem. I studied the problem and I got into it and I got into it and I said, there's something wrong here. And John Bell himself, he said, there's got to be something wrong with this. He said, if the laws of physics are different at the small scale of 10 to the minus 48 power photons, photons, than they are at the scale of bowling balls, then there's got to be some scale at which the laws of physics change. And what could that scale be where they change? He said very clearly, he said, either we're going to find out, or as I suspect, we'll find out that there's something wrong with this. I don't know what it is, but I suspect we'll find something wrong with it. And I'm saying somebody coming out of nowhere, not a physicist, a probabilist, a mathematician. I'm saying, I found out what's wrong with it. This is what's wrong with it. Read the book and you'll see. That's what it is. And the problem, the error gets expanded and expanded and expanded. And I assessed that error in 7 different chapters that discuss many aspects in great detail. The finest detail was not of interest to the general reader, but the idea of what's going on with the problem, that should be of interest to a general reader. And I wrote it for general readers. It's fun, it's funny, it's remarked, and it's mathematics.
Well, and a lot of people love mathematics, and obviously, if the math, as you say, adds up, it's right. So, the book revisits the ideas of the hidden variables in quantum mechanics, as you really said. How do the variables help explain some of the mysteries of this quantum behavior, as what you're talking about? Because I think you've explained some of it, and I may be asking this question again, and you may feel like, hey, well, I already answered this question, but maybe you could approach it in another way where the people listening are like, okay, I get it. He really has said that these variables were the variables. I get the variable about the photon and going to each end and the mathematics of each of that. I think you did a great job of explaining that. What could you add more to it, or are we good with what you've already given?
The thing about hidden variables is that they're hidden. People are trying to figure out what they are. There's a lot of people who are thinking, well, maybe this is going on, maybe that's going on, maybe that's going on. There's a whole literature about that, which this book does not discuss. That the variables are hidden, and we don't really know what they are yet. But the way the hidden variables work is, suppose that you did a bowling ball and you knew about the angle of the direction of the direction of that at which you're rolling the bowling ball. You knew the acceleration of the ball. You knew the rate of the spin, but you didn't even think about, and you don't even know about, the coefficient of friction of the bowling balling lane. Well, bowling balling lanes, when they're prepared and they're brand new, well, they're like glass. There's no friction at all. Well, there is some friction. There's no, but now since it's a bowling ball where you and me and all these armies are bowling on the thing and we're bashing the ball and the surface of the bowling lane is not perfect. What is it?
Right.
Well, if you didn't even think about that, well, that's a hidden variable that if you didn't think about that coefficient of friction, then you would find out that the laws of physics wouldn't tell you exactly what was going to happen because they didn't have involved.
Now, that's a very good explanation that the average person who's listening to this can understand, because they haven't looked at the hidden variables. And I think if there's one thing they could take away from this interview is the fact that the hidden variables, all of them, need to be looked at to come up with the right formula to determine what's going to happen. That's true with anything in life, right? You think, hey, look, I drive a car which is electric. Well, here's another factor, right? And this is a simple one I think my listeners would really get. So all these electric cars say, well, you can get 300 miles on a charge, right? Or they're close to it. But the reality is, it depends on the speed that you're driving at. It depends on the road resistance that you get. It depends on the weight that you're carrying in the car. It depends on all these variables. And everybody says, well, my car didn't get the 300 miles. No, it didn't get the 300 miles because you're at all of these other factors, and that battery that you're depending on is actually, it's drawing much more energy to do that. So climbing a hill, doing all the things that it has to do. And so, yeah. And I think that's a really great example for people to say, I understand better, but the variables, because I can tell you one thing: I've never gotten 300 miles out of my 300-mile charge. And there are times when it can be disappointing because you're like, "Oh boy, where's the charger?" Right? So,
Yeah.
so let's look at it this way: you have this personal journey that you've taken on, and that's taking on this scientific establishment with your findings. Um, have you faced, and if so, I know you faced some resistance, um, of the mysteries of the quantum behavior, or are people in acceptance of what you're actually articulating through your book and your talks and everything else?
Yeah, yeah. No, there's generally resistance because the people will say, "We already know about this. I'm not even going to read your stuff. We know this is all these. We know about this, and we're not gonna." Well, I'll tell you this, Greg. I'm a member of the American Physical Society, and this coming March in Anaheim, California, there's going to be a global meeting of the American Physical Society, in which 15,000 physicists from around the world are going to come.
Really?
And everyone who's a member of the society, of which I am a member, have a right to make a 10-minute presentation on whatever you want. There are all these categories. I mean, there's a huge booklet of what are all these talks are going to be about. Well, I'm going to be there and I'm going to talk for my 10 minutes. I will be able to talk even faster to these people because the people who will be listening to my talk, they will know all about Bell's inequality. They will all know about polarization of light. They will know about all this stuff. And I'll be able to talk even faster than I'm talking when I'm talking with you.
Well, I'll have to come to that because I don't live that far from Anaheim. So you'll you'll have to remind me, and I'll meet you in person.
That's okay. Well,
And
you'll have to pay $350 to get in the door.
that's okay. We can do that.
Oh, great. Oh, fabulous.
So-
Okay. I'll meet you in person in Anaheim. It's March 16th to 21st is the meeting, and I believe my talk is at 11 a.m. on March 17th, I believe.
And is that this 2025, this coming March?
Yes, yes.
Okay. All right. So look, for the layperson,
Yeah.
quantum mechanics can seem somewhat esoteric. What would you say to someone who feels intimidated by this subject, but is curious about its significance?
That's okay. Okay. Well, I'll say this. When people send you get an email and says, "Oh, Greg, congratulations, you've won $3 million that's been awarded to you by the United Nations survey for people who are interested in personal development." And all you have to do is to click on this reply and tell us your bank account number, and you'll be fine. Or if it sounds too good to be true, and what people say about these scammers, if it sounds too good to be true, it is too good to be true. Well, I'd say this about people who think that, some, not everyone, but a good number of these quantum physics people. I sent a paper to one place and he said, anybody who knows anything about quantum mechanics has got to come to grips with the fact that when you're not looking at the moon, it's not there. The moon's not there unless you're looking at it. Meanwhile, the tides are pulling the ocean in and out and out. You're not looking at the moon, but these people, there's not just that. Then there's other people who say, "Oh, there's not just this world we're living in. There's a whole bunch of worlds. There are many. It's called the many worlds hypothesis." They say there's many, all the ways the world could possibly be. Well, it is all those possible ways, and we're just in one of them. But there are all these other ones too. Now, these things are crazy. If you hear things about quantum physics, don't be so I would say to someone who don't be intimidated by mathematics. Mathematics is a language. How about you? Do you speak French? Do you speak Hindustani? Do you speak Italian? Do you speak whatever language you like to talk about? You don't speak those languages? Well, you can't understand what people are saying. That's what mathematics is. Mathematics is a language. It's a language for talking about things. Some languages are good for talking about some things, and not for other things. Some are good for those other things, but they're not good for this thing. So
Very good.
Don't be intimidated.
Well,
But-
look,
Go ahead.
you have ideas you presented in your book, influences other fields such as technology, you said philosophy or education. Can you speak with the listeners about that? I mean, the one you just talked about, If you're not looking at the moon, well, then the moon's not there. There are lots of those theories around what I would call quantum physics, right?
Yes.
So, um, how can the ideas that you presented in this book influence these other fields, such as technology, philosophy, or education?
Mm, I'd say, well, aside from the details of what's wrong with the understanding of quantum physics per se, there's another feature that the physicists refer to as the feature of entanglement. The entanglement of photons. This photon's entangled with that photon. And it turns out that their sense of of entanglement comes from their misunderstanding of the meaning of features of the probability distribution that characterizes the probabilities for yes, 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 no, no, yes, no, no. Those probabilities of yes, no are the same as the probabilities for no, yes, where these two photons go through. That's a feature of symmetry of the probability distributions. Bruno De Finetti referred to those as exchangeability. But we have exchangeable opinions about the behavior of these two photons, just like we have exchangeable opinions about the wheat yield of 2 acres of Kansas that are separated by 300 miles apart. Kansas looks the same everywhere. You're going through the Kansas, well, it looks the same everywhere, but it's not the same everywhere. This is this one, there's that one. This one's close by to a nature reserve where all the birds come and hang out. That one's not. Well, if you say pull up 2 acres at random, you don't know which one is which. You don't know anything about that. Blah blah blah. So it's not that the acres are entangled; it's our opinions about the results of the 2 acres are entangled, and the same with our opinions about the activity of the photons at these two.
Well, I think when we had our first one, I think one of the things our listeners could probably understand, and because you're a studier and a teacher of statistics, is the whole thing around predictive analytics.
Yes,
I know this isn't part of the book per se, but this is something I think our listeners could understand a little bit better. What would when you talk about these probabilities, and I think this is something very real for listeners to want to understand. And let's say an insurance company uses predictive analytics to say there's going to be fires in Los Angeles, so we're canceling all your homeowners
Right
insurance.
1 sec. Let me just grab one other book. Hold on.
Okay.
That's okay. Great. Good. I'm back. I just wanted to hold up this other book because this other book is the major book of my professional career: Operational Subjective Statistical Methods: A Mathematical, Philosophical, and Historical Introduction. Now that book people can get in a library. Any university library will have it, and many other libraries as well. You can get it. You can still get one. A used copy online, I think. Anyhow, blah blah. The issues about predictive analytics is that the objective theory of probability says nature is random. Things happen by chance. There's some probability that that fire that started out last week and that we damped down, there's some probability that it will jump up again. They say it's random whether it'll jump up or not. What we're interested in is the probability. The real things are the probabilities. What we need to do is to estimate the probabilities. And the way that we'll estimate them is we'll find out all the other fires in history that we know that are just like this fire, and find out after they were down to this extent, how many of them started up again, how many of them, and we're going to estimate the probability. That's what Bruno De Finetti. There is no probability. It's going to jump up or it's not going to jump up. You don't know, I don't know. Your probability represents your uncertain knowledge, mine represents mine. Neither of us are right or wrong. We're just saying what we think. But some people are informed by all sorts of other fires. Some people are not, and so your probability that's where you are. This is where I am. Probabilities are not things to be estimated because there aren't any probabilities. What we want to assess is there going to be a fire or not?
Right.
But we're not interested in estimating probabilities. We can do scored sequential forecasting. What that means is we make forecasts of things that we don't know what's going to happen next. A bit easier example is, how about dairy cows? You got a herd of 1,000 Holstein Friesian pure purebred dairy cows, and they're all heifers. They've just given birth to their first child. How much milk are each of them going to give? You don't know. I don't know. We neither of us know. But your knowledge of dairy cows, you know something about dairy cows. Do you drink milk? You've seen a cow at the fair, at the county fair. You know they're big. How big are they? How much does the dairy cow weigh? You don't know. I don't know. My understanding is probably closer than yours because I have studied things about dairy cows for my statistical reasons. But the point is that we don't know what the yields of these 1,000 dairy cows are going to be tomorrow. Neither you nor I know. We can put some probabilities for these are what my probabilities for these yields are. This, your probabilities are that. Now, suppose that we can observe the first 10 dairy cows. This one being milked twice a day. This one gave 90 pounds. That one gave 102 pounds. This one gave how many the milk was measured in pounds. And
I understand what you're saying. I guess my question might be because there's a whole lot of believers out there and a whole lot of people using artificial intelligence, which is collecting data and analytics from all over the internet, right?
That's right.
And so my question for you would be is, do you believe that people might be getting a little bit closer with this predictive analytics with maybe a more reliable or an abundant source of data and which is being fed in to something like AI to come up with a mathematical model that might have more accuracy? And I mean, if you go way back in time, we had a hard time getting those analytics from around the globe. Now we're able to, with pretty much the push of a button, come up with all kinds of mathematical analytics. What would your comment be? And what's one?
You're right on. That's our hope that we would get better predictions of things that interest us. What do you mean by better predictions? I just said that you have your opinions. I have my opinions. Probabilities represent our uncertain opinions. Well, if you're interested in finding out what you think or what I think, how about you express very carefully your opinions via probabilities for a sequence of observations, and your probabilities are yours, mine are mine. How about if we give each of us a score? When you don't know exactly what's going to happen, so when with the accident things would happen, you didn't say it was that or it wasn't that. You said it might be this, might be this one. There are ways that it's in the theory. They're called the theory of proper scoring rules. This is a statistical theory that developed. It was mainly motivated by a really great American statistician, was Leonard Jimmy Savage. He was called just before he died. This was his last work, but it's a topic that has developed, and I'm quite interested by that. That's what we do. You make sequential forecasts. Somebody else makes different sequential forecasts. Well, let's score your forecasts. Let's score my forecasts.
I see. Well, that brings. I mean, there kind of really gives the listeners a little bit more of a understanding. Now, look, you've got this book, and to kind of wrap our interview up, you're taking people through this journey that you've done of just plain wrong. That Bell's inequality is wrong. This theory.
This defiance is wrong.
Well, the defiance of the quantum theory and the defiance of Bell's inequality. Yeah. So tell me, what is one big takeaway that a listener would get from your book, Just Plain Wrong? And what do you hope it will be that, hey, really, people should question, people should look for the variables, people aren't looking for the variables? What might be the big takeaway for somebody who's average after they listen to this podcast?
Okay, well, the people who are looking at the variables, those are people who are doing experiments at the nuclear accelerator in Europe and then at Stanford and all these various places. Those are the people who are dealing with the physical situation. What someone can take from this is to realize that science is not a bunch of facts that we know for sure, and that science is a representation of our best considered opinions of the people who've been studying this thing the most possible, much more than you have. The people have been studying it, and they're communicating with each other, they're criticizing each other, they're discussing things. But scientists can be wrong. The mainstream idea can be wrong, and when you make a mistake, it's one thing to say, wow, I made a mistake. I wanted to learn something from. The other one is to, when someone points out the mistake, is to repress it. We'll repress it. We'll keep that stuff out of here. Don't let anybody read that kind of stuff. Well, I'm gonna no. That's when you make a mistake, and someone points out the mistake to you, then you think seriously about it. You might then say, "Oh, well, your understanding my mistake is wrong for these reasons." You can discuss, but be willing to discuss. When you say when you have an idea that you're living in terms of some world where you've put it all together in a certain way, when somebody challenges you, think about it and discuss it and admit that you're wrong if you are wrong, and revise your opinion. That's what I think people should learn from. And
Well, I
in
think
general,
that's a great takeaway for anybody, whether it was this theory or any theory. It's really about life in general, because you're saying, look at this side, look at that side, look at the variables, weigh out the differences, and in the end, we're all going to come up with our own opinion, huh? So,
agree will agree, and many of us will agree with that. Many of us will agree. It's just because we agree doesn't make us right. But and if you take science seriously, unless you have something particular to say that's critical about it, well, you go with what the scientific opinion is.
well, obviously, in this one, Frank, there was a consensus that Bell was right. And, as you go down the road, and until you've kind of come along here, you're saying, yes, others have actually challenged it as well, but you're challenging it in a big way by writing a book and saying, hey, this is wrong. And I just want to acknowledge you for that, because, sometimes there aren't a lot of people that will stand up in the scientific community to do that. But do get this book if you have interest in Just Plain Wrong, The Dalliance of Quantum Theory, and The Defiance of Bell's Inequality. This would be a good book for you to read. You can get it off of Amazon. You can certainly, that's the best place that you could go ahead and pick up a copy of this. Frank, it's been a pleasure having you on the show to speak about your book and your other book as well. And you might not be able to get that other book as readily, but he did mention it during our conversation here. And you could certainly get it at the university, or you'll probably find some used copies around as well. And I look forward to meeting you in March in Anaheim at the conference. And thank you for being on the show.
Yeah, good. Well, I'll be in touch, Greg. Thanks very much. I enjoyed talking with you.
I enjoyed it as well.